All right. So the time has come now. I'm going to step aside and we're going to let Mr. Professor Henry Chang to step forward and ask him to please let us hear his his take on Buddhism through the lens of a scientist. I'm going to ask Jin Shi to do the introduction because he knows Professor Zhang. And furthermore, one of our dear friends here at the Berkeley Monastery, Fang Jiahua, was and Liang Yuqin were classmates with Henry. So that's a good enough recommendation for me. So 果然我就请这个金融师就为大家介绍我们接下来的一位这个物理学家，就是 Henry。那么我所知道的 Henry 是我们 Berkeley Monastery 这个居士放家华的这个同学，认识很多年，还有梁玉琴，所以那个一定是很难得的一个佛缘呢。So, Jin Yong Shi, would you like to please do the introduction? And I'll come back at the end and transfer merit.
Okay, I'll try. Henry, would you like to turn on your camera? You mind?
Okay.
Anyway, just introduce Dr. Chang, Dr. Zhang briefly. He is a retired professor, I think, from Danjiang University, and he has been teaching there for many years. 张教授他是从台北这边的淡江大学物理系已经退休，在那边教了很多年书。那之前刚刚石法师讲的，他是台湾这边的大学东吴大学的物理系毕业 ，and he graduated from the physics department from Suzhou University, right, Taipei,
Yes.
and got a bachelor degree in physics. Then he moved on, came to US to study at New York University, at a PhD degree in physics. 他然后到美国来念书，在纽约大学拿了物理博士，然后会在美国这边工作几年以后，再回到台湾去。So he worked in US for a few years, then moved back to Taiwan to teach there. I think, as I know, he actually met the Venom Master and took refuge under him in the early 90s in ITI. 张教授他是亲自在上人的座下皈依的，在90年代，在我们的那个易经院那里。那我就他过去有几年有到圣城来待了有几个月的时间，暑假的时候。Several years ago, he spent a summer in CTDP attending the translation seminar and other activities. Okay, so I'll let Dr. Zhang to start to speak because time is very limited. 我就这边让张教授开始讲了，因为时间很短。
Hello.
Please go ahead. Yeah.
Amitabha, can you hear my voice?
Yes.
Okay. 阿弥陀佛，大家好，谢谢金勇法师啊，谢谢石法师啊，让我到这边来分享一下。那么主要要讲的就是这个聚变能量啊，这个大概1个多月前，金勇法师他问我说能不能够讲一讲最近的这个核聚变技术上的突破。其实我一直没有去注意这一方面的事情，因为核聚变这个理论已经知道很久了。那么在过去的几十年当中，有很多这个号称突破的结果，后来都发现只是错误的实验啊，所以我个人也一直没有在注意这一方面的事情。Hello everyone. I'm pleased to be able to give a talk today in here. Thanks to Dharma Master Heng Shuo and Dharma Master Jin Yong for inviting me. About more than a month ago, Dharma Master Jin Yong asked me if I could give a talk about the recent breakthrough that in the field of nuclear fusion in Lawrence Livermore National Laboratory. Since I'm not specialized in this field and I haven't been looking into this for quite a long time, because in the past couple of decades, we've heard a lot of announcement on the breakthrough in this field, and most of them turned out to be false announcement. But this time, since the
Henry，
announcement，
你麦克风不用那么靠近嘴巴，
OK，
靠近嘴巴呢会有一些杂讯。
OK， 好。Okay, since this time it looks different because the announcement was given. I couldn't control my. Okay, here it is. Can you see this view graph? All right.
Yes, we can see that.
Okay, because this time it looks different because the announcement was given by the Secretary of Energy of the United States herself. So on the 13th of December of last year, they held this press conference, and this is part of her comment. This is the most impressive scientific feat of the 21st century. So this is different. I then look into some of the literature and reports and found that this is really amazing performance. OK， 谢谢金庸法师他的邀请。那么后来我发现这次的突破大概比较特别，所以就稍微注意一下啊。这个就是他们发表这个记者会的这个场面。他们在12月13号去年，那么他们就发表了一个记者会，由这个能源部的部长亲自发表。那么他说这个发现这次的核聚变的这个技术上的突破是21世纪里面最重要的一个科学的这个事件。那么我就开始去了解一下它里面的这个细节看一些相关的报道跟一些学术文章，发现它的确是不同这一次真的是非常非常了不起的一个突破。那么我们来看看这个要讲这个事情我想就先提出2个问题第一个这个在这个劳伦斯Lawrence Livermore National Laboratory 里面的这个突破到底是什么第二个问题就是我们距离商业化的核聚变能量，也就是这个核聚变发电还有多久可以实现。Okay, let me bring out these 2 questions. I think this is important in order to talk about this breakthrough. First of all, what is the breakthrough in LLNL? And secondly, how far away are we from commercial fusion? Okay, actually the experiment was performed on the 5th of December in the National Ignition Facility, which is inside of the LLNL. What they did is they conducted the first controlled fusion experiment, and this is very important. This is the first time a human being was able to do this, because the theory was there, and the fusion experiment has been done before, but it was done by detonation of the hydrogen bomb, which is not considered a controlled fusion experiment. And after that, the progress was just incremental, and not like this one. They achieved the fusion ignition. Okay, fusion ignition meaning that scientific energy break even was realized, which means that the energy sent in to trigger this reaction is the same as the energy get out from the reaction, and they actually did a much better performance, because they sent in energy of about 2 megajoules, and they got more than 3 megajoules out of it, and this is a very good result. 那么实际上这个实验呢，这个突破是发生在12月5号啊，去年的12月5号。那么在这个国家点火做这个设施，这个是一个单位的名称，它是在劳伦斯国家实验室里面。那么他们所做的事情就是他们第一次的完成了这个可控的核聚变啊。那么可控的核聚变，这是人类第一次能够达到。那么这中间当然它这个叫做聚变点火啊。那么它的这个定义就是说送进去的能量跟获得的能量能够 break even， 也就是能够打平能够相等。那么他们当然做得更好，他们送进去2.05啊，就是这个叫做100万焦耳，那得到了3.15百万焦耳的输出。那么这个就是一个很重要的突破。那么接着我们就来了解一下那么什么叫做聚变能量啊？聚变能量，那么它这个其实就是我们的太阳所产生的能量，或者其他恒星所产生的能量。Okay. Now let me explain a little bit about the fusion energy. Okay, fusion energy is the source of energy of the central star, including our sun. If we use this to generate electricity, then we have all these benefits. Okay, abundant energy, meaning that for the same amount of fuel, the fuel of fusion contains more energy than the regular fossil oil or coal. Okay, and much more. It's like a few million times more energy is stored in this fuel. And the sustainability, meaning that the source of this fuel is basically unlimited on the earth, because most of them you can get directly from the seawater. And there's no any greenhouse effect gas emitted. Okay, so no CO2. There's no long life radioactive waste, meaning that the waste is non-radioactive. It's not like the nuclear power plant that is running in many places in the world, which has very harmful waste, which are radioactive. And the next one is limited risk of proliferation, which means that you don't have to worry about the problem of developing this technique, like the fission power plant that we are currently using, because for those plants you need to use fuel which is enriched. And if you can enrich radioactive material, which means that you can use that to build atomic bomb. So this is dangerous. And fusion can limit this problem. And then there's no risk of meltdown, like what happened in Chernobyl and recently in the 3 Mile Island of Japan, because this kind of power plant, when there's any problem, it would just shut itself down. Okay, this is all the nice thing about it. So 对这个核聚变的能量有什么好处？第一个，它的能量跟太阳产生能量的原理是相同的啊。那么核聚变呢，它有这么多个好处。第一个就是它所含的能量比一般的石化气体或石油所含的这个能量要大。以同样的量来讲，它这个含的能量大概是一般石化类燃料的几百万倍。第二个，它这个取之不竭，用之不尽，因为它这个燃料可以直接从海水里面提炼。那么第三个呢，它不会放出这个温室效应的气体包括二氧化碳。那么同时它也没有放射性的这个废料产生那么同时它也可以限制这个滋生性的这种燃料。因为如果说是要用目前的这种核电厂来发电的话，它的燃料必须要做一个纯化跟处理。那么处理完之后，这个燃料用来发电的燃料也可以做这个原子弹所以这个是一个防止核扩散来讲是一个问题所以这个融合的这个发电不需要用到这种燃料最后呢，它也没有这个被这个 meltdown， 就是像山里岛那种这个融化整个反应炉融化的问题。因为这样的反应炉它只要是有问题的时候，它的燃料就用掉就没有了它这个燃料不会把其他的东西给烧掉。所以这些都是它的好处那么所以这个是一个非常理想的能源。那么我们现在来介绍一下这个核聚变简单的介绍我们现在看看这个带有一个正号的这个颗粒，我们叫做质子质子的话，它是这个氢原子的原子核就是一个质子那么这个质子如果它带了一个中子，那么它就叫做同位素它还是氢，但是它比较重一点，它多了一个质子，就叫做这个氘。那么氘我们这个底下2撇表示它是有2个核子那么如果它多了2个中子，那么它一共就有3个粒子在核里面，那么我们就用氚来表示那么这个氘跟氚是核融合的燃料，这2种这个原子核进行核融合是最容易的那么因为它是最小的，那么它们如果发生反应之后发生融合反应之后，它们就2个融而为一变成一个原子。那么这个时候，这个原子里面就会含有2个带正电的质子。这个时候，这个原子就不再这个原子核就不再是氢了，它变成了氦那么这个氦里面有这总共3个中子都跑进去的话，这个氦就不稳定，它就会放出一个中子，然后变成一个稳定的氦原子那么这个就是它的反应。那么同时它放出中子，同时放出很大的能量那么这个是它的反应式，这个 D 代表氘 ，T 代表氚那2个合在一起之后变成氦，放出一个中子以及大量的能量那么这个是它的反应The nuclear fusion, we can explain it with this view graph. The one with the particle with the plus sign is proton. Okay, one proton is actually the nucleus of hydrogen. If this regular hydrogen, if you add one neutron into it, it becomes an isotope of hydrogen. It's still hydrogen, but it's heavier. It's called deuterium. If you put 2 neutrons in there, then this nucleus becomes another isotope of hydrogen. Okay, it's called tritium. And the 2 nuclei can be melt together or fuse together or fusion into a bigger nucleus with 2 protons. When you have 2 protons, it is called helium. Okay. Now the 3 neutrons can also be stick into this nucleus, but it's not stable. Okay. So one of the neutrons would be released, and then you will get the product, which including the helium atom, 1 neutron, and a tremendous energy. Okay, this is the equation of the reaction. D plus T becomes helium plus neutron plus energy. So this is the nuclear fusion. But to do this, it's not very easy, because one can see that you are putting 2 positive charge together. Okay, they have tremendous repulsive force, and you need to overcome them. Therefore, you need to put a lot of energy in, and this is why it is so difficult to do. Now, the ignition, meaning that if we want to make this happen, make this reaction happen, then we need to satisfy these conditions. Okay, there are mainly 3 conditions. The first, particle density of the plasma has to be very dense. Okay, which require a very high pressure, as high as the center of the sun. Actually, we need more than that. Okay, so the pressure has to be higher than the pressure at the center of the sun, which is a few million times the pressure at our atmosphere. Okay, so this is very, very large pressure. And then you need to heat it up to a very high temperature, 130 million degrees centigrade. Okay, so this is very high temperature and very high pressure. And then the most important thing is that the confinement time, because the reaction, if according to what they reported in this breakthrough run, this experiment, the fusion lasts only 1/10 of a billionth of a second. So this is a very, very short time. And you need to make these 2 conditions happen at the same time. And you have to be as precise as this, okay, at this moment. So this makes it very difficult to do. So that's why it's very amazing, and they did it. Okay. 核聚变的点火条件，它是需要一个高压、高温，那么同时它要精准的同时发生啊。那么这个高压是多高？比太阳中心的压力还要大，那是地球大气压力的好几百万倍啊。那么温度要130个百万，也就是13000度啊，13000度摄氏度。那么这其实什么度都差不多了，到这个尺度的时候。那么最重要的是这2件事情要同时发生，因为整个融合的过程，以这一次的突破啊所做的实验来讲，它在这个这个叫做这个10亿啊 ，billion 是10亿，那么在1/10，所以它是100亿分之1秒之间就完成啊，所以这个要非常准确。因为达到高温跟达到高压都不是容易的事。As we said, the extreme condition at the high pressure and the high temperature, both are not easy to achieve. Okay, now this is the beauty about this experiment. Okay, in the NIF, National Ignition Facility, they use this inertia confinement fusion. Okay, this is a technique called inertia confinement. Okay, this is relatively new technique, because in the old experiment or old plant, they when they do fusion experiment, they use magnetic confinement, which I would go over a little bit later on. Okay, now this is a canister made from gold. They put deuterium and tritium fuel in a capsule. The capsule size is about the peppercorn grain. Okay. Now they put it in here. This is the capsule containing the fuel, and this is the canister made of gold. Now they want to heat it. They use this indirect heating method. Okay, they use laser beam, a total of 192 laser beam. The laser beam doesn't hit the fuel directly. Instead, it hit it on the canister wall because the laser is very energetic. When it hits metal, it creates X-ray. The X-ray is also energetic. The X-ray will be confined inside of this canister, thereby heating the capsule. Okay, and then if it's hot enough, it'll explode. The outer shell of the capsule will explode, and this capsule is made very elegant. When the outer shell explodes, the inner shell implode. Okay, when it implodes, it would squeeze or compress the fuel inside of it, compress it until the size is about the thickness of a human hair. At that point, the fuel will be hot enough and pressurized to what it needs. And at this extraordinary temperature and pressure at the center of the capsule, the fusion would be realized. 那么这个是核聚变的所用的，这次他们在这个国家点火装置里面所用的方法叫做惯性这个约束惯性约束。那么这惯性约束的方法是比较新的方法。那么他们做的方法是这样子，他把这个核燃料就是氘跟氚包在一个胶囊里这个胶囊是一种特制的胶囊然后这个胶囊放在一个金做的这个罐子里，然后他们用192道高能量的雷射光也就是激光打在这个罐子上，它不是直接加热到这个胶囊，它打到罐子上，然后这罐子受到高能量的雷射这个撞击之后在里面会产生 X 光这 X 光就会去对这个胶囊加热加热到一定的程度的时候，够热的时候，这个胶囊会爆炸。这个胶囊的制作是很特殊的，它的外壳向外爆炸，内壳它会向里面压缩，因为这个反作用力的关系，它这个达到这个温度的时候，它一爆炸一压缩，那么里面的燃料通通被压到跟一个头发的这个粗细度差不多那么原来它的这个胶囊的大小就像个胡椒粒那么大，那么一瞬间一压缩到这么小，这个时候它这里面的这个条件就达到了，比如说高温极高温跟极大压力同时达到，那么这个时候核聚变就发生。Okay, now let's look at the energy budget of ICF, inertia confinement fusion. Okay. This is the figure that I use, but the number is different. This is older number. Okay. Now in this run, this breakthrough, they use about 5 megajoule here. Okay. Now the 5 megajoule is what they pull out from the grid. Okay. They use this much energy to start laser, and the laser output is only 1% of it. Okay, it's about 4 megajoule. And then this laser has to be triple frequency. Triple frequency means that they increase the frequency of the laser beam from red or infrared into blue or ultraviolet. They need a higher energy beam, so they need to increase the frequency, but along the way they lose more energy. And then when the laser beam hit the canister of gold, it transferred the laser beam into X-ray. They lose more energy, and then they focus all this energy in the fuel, and the ignition is completed. After that, they get this much energy out. Okay, this is the original plan. But what happened is that they used 500 megajoule. They transferred to the laser output. There's only 2.05 megajoule, and then this is what considered to be the input energy of this reaction, and this is the output energy. So this is called scientific break-even, or the efficiency is compare this output and this input, not the original input that pour out from the grid. Okay, so they consider this is the input, then they're doing pretty well. Okay, this is the energy budget. 那么这个能量的收支啊，这个核聚变，他们现在是从电网上取的能量，大概有500megajoule。那么经过把它这个启动雷射啊，然后这个激光啊，它这个激光输出的能量只剩下1%。那么再把它3倍频之后啊，它只剩下1.8。那么再把它变成 X-ray， 它变成更少。那么以现在来讲，它这个3倍频就剩下是2.05。那么，然后打到这个目标上，最后得到聚变能量啊，那么是差不多3.1。那么从这里来看，我们以这个能量为输入能量，这个能量为输出能量，所以它这个在这个融合这件事情来讲，它是有能量的增益啊，也得到更多的能量。那么实际上它用的能量当然是在这里啊，这么多。那么如果说以这个来当做你的输入的话，其实你这个输出的能量是不到1%。那么这个是能量的收支。Now let's look at the mission of NIF, National Ignition Facility. They want to develop the technique to do power generation. At the same time, they do material study at the extreme condition. They also do weapon maintenance to maintain the existing stockpile of nuclear weapon. But this setup is not ready to become a power generator. In other words, they have a lot of improvement or modification to do in order to generate electric power. OK， 那这个惯性约束它用在发电上的话，在技术上可能还有很多地方要改善，因为他们还有其他的这个任务啊，他们做了这个点火之后啊，他们可以用这个极端的条件来测试材料啊，来研究材料的这个性质。另外，他们对这个核武器的维护啊，那么也有帮助。这个是他们的功能。那么实际上，我们如果要回答第二个问题，我们什么时候可能有商业运转的这个核聚变发电厂 ？Okay, to answer the second question, we need to study this. Okay, now for ICF, the gain is about 1.5 at the current experiment. They want to make the gain to greater than 100 in 2030 or before 2030, because they want to be able to use it to create to generate electricity, and they plan to have a commercial power plant in about 2050. Okay, this is what they claim. Now, 这个惯性约束的它的争议啊，目前是1.5，那么他们希望在2030年之前把这个争议提高到100，到2050年开始可以有一个商业运转的这个发电厂。Actually, in the for the same fusion, nuclear fusion, there are the other type of technique called magnetic confinement. Magnetic confinement and this reactor is called tokamak. Tokamak was created. The first tokamak was created in the former Soviet Union in 1958, and then up to now the improvement was incremental because it's very complicated. Okay, now this is the ITER, International Thermonuclear Experimental Reactor. It's the largest plant in the world. The reactor is being built in France. Participating country including China, European Union, India, Japan, Korea, Russia, and United States, plus 30 other countries. Well, these countries would collaborate to do this, and their main mission is to do power generation. So they use magnetic confinement, and they handle a plasma, which is the fuel in a much larger scale. This is the image. As you can see, the magnetic confinement would confine the fuel inside of the donut-shaped cavity. 那么国际热聚变这个实验的反应炉啊，它的主要目标啊，就是要用来发电。那么第一个，他们这个反应炉叫做 tokamak 啊，这个第一个是在1958年的时候就制造出来，在苏联。那么现在这个有这么多个国家啊，30几个国家合作，在法国建造一个叫做 ITER 的这个反应炉。那么这个反应炉，他们这个用这个磁场来做这个约束啊，就是让这个燃料不能够碰到任何的这个实验部件啊，因为一碰到就融化，它的温度非常高。Okay, so this is the view graph shows that how a magnetic confinement works. You can see basically there are two magnetic fields. This is one magnetic field inside the donut, the huge donut-shaped cavity, and the other is this direction. It goes this direction. So these two magnetic fields would add up and becomes a helical magnetic field. It goes like the helix curve. So that would contain the plasma inside of the cavity, and then they use outside heating method to heat up the plasma, and then make it fuse to get the ignition. In 1997, GAET, which is tokamak in France, this is their world record. With 24 megawatt of input, they got 16 megawatt out, and this is not good enough because there's no gain. They plan to be able to do a 10 times gain in 2040. Okay, this is more like the power plant type of reactor. 那么国际磁约束这个磁聚变这个反应炉啊，它用磁约束。那么磁约束呢，基本上有两个磁场，一个是沿着这个大圆的这个方向的磁场，一个是围绕这个圆圈这个大圈圈的磁场。那么这两个磁场加在一起就变成一个螺旋状的磁场，它可以把这些反应物把它限制在这个空腔里面。那么在1997年，法国的 JET 这个反应炉已经做出25这个mega 瓦特的输入，那么功率可以得到16 mega 瓦特的这个输出。当然这个没有争议，他们准备在2040年的时候能够达到10倍增益的这个反应炉。那么因为它这个主要
时间差不多了。
OK， 这是最后一张。OK，那么这个是这个一个示范的这个反应炉，那么它可以直接装到我们现在存在的电网上面，直接发电。OK， 那么我今天的介绍就到这边啊。 This is the demo machine. Okay, hopefully in the 2050s it will be running. Thank you very much. That's all I have to say tonight.
Thank you so much. I'm running out of time, so I don't think we have time for questions.
Okay, that's all right.
All right. Yeah, fascinating. This is profound, and we can all cross our fingers and hope that that the predictions are true.
Yes.
So, Professor Chang said that usually these kind of announcements don't turn out, but this one may be different. Certainly, the Department of Energy thinks so. So,
yes, exactly.
Yeah, good. All right， 难得啊，有这么一个精彩的一个专业的这个报道，Yeah， 难得了。Okay, yeah. So thank you, Professor Chang.
You're welcome.
Yeah， 感谢张教授啊。那么我们就会上功德了。金勇师 maybe next week I'll have to find a replacement because I think I'll still be traveling. So.
Yeah, okay. I wonder whether the volunteer teachers, they can double up and use the time.
Maybe so.
Yeah, starting next week, there are 6 volunteer teachers. They are going to share their experience. So,
Okay.
yeah, I'll see if they can do that.
好的 ，OK， 那么我们就用这个药师观顶真言当我们的回向。那么各位向华严经上的第6回向的菩萨来发自己的回向愿。So we'll transfer merit. Please imitate the Bodhisattva of the 6th transference. Make your own wish. Send out your merit and virtue. Here we go. Make your own wish. Arahate samyak sambuddhaya Tathata Saji Saji Saja Samukate Swaha 再来 Om Namo Bhagavate Saja Durya Pravarajaya Tathagacaya Arahate Samyak Sambuddhaya Tathata Om Saji Saji Saja Samukate Swaha 再来一次 Om Namo Bhagavate Saja Guru Vaidurya Pravarajaya Tathagacaya Arahate Samyak Sambuddhaya Tathagacaya Om Saji Saja Samukate Swaha. I hope all of your transference wishes come true. And meanwhile, we can bow to the Buddha and to our teacher. 我们现在向佛礼、三问熏礼，然后呢，向玄公上人就顶礼3拜。Bow in respect to the Venerable Master. 好的 ，OK, that will do it for us for